Hi, Toby.
Hello,
Hello.
how are
Right.
you?
Yeah, good. Good. Thank you. Right. I hope I hope Easter will not affect the number of students. Well, I mean, it certainly will, but hopefully we have some students. Right.
I think I need to be host to share screen because I've got the iPad.
Yes, I will make you host.
Thank you.
So which one? I see two of you.
The one that's not, the one that's blank. I don't know
Oh,
which one
that's
that
blank.
is. They're both on the same account.
Okay. Make host. Right.
Okay,
Make
let's see if
host.
yes, whereas
Perfect.
okay,
Excellent.
right. This is all working.
Okay.
How many students are there usually?
We don't get much, but we do record these sessions. We usually get for year 13 on Thursdays, we get 4, 5, 6 students.
Oh, okay. How much back and forth is that? As in, do I stop to ask questions or is it?
As yes, the way you choose. I normally ask questions and get answers in the chat. Oh, hello, Adam. That's one of our regulars. Good. So even if there will be a few students today, we still record it and we put it out there so and students watch it. So
Okay.
yes, I think lovely weather today might affect the numbers. All right. So I'll be popping in and out. I'll send you my phone number just for emergencies if something goes wrong. I'll
Okay.
send it to you by email.
Okay. Ooh, that's not what I meant to
Oh,
do.
I guess we can start. It's 6:01. Yeah.
Okay. Do you want me to just get started or?
Yeah. Well, yes. So welcome a student. Well, we just have one student for now. Hopefully, some more join later. Join. Okay, we have more students. Okay, so welcome everyone. Let me introduce Toby. He's done a few assignments for us, and brilliant physicist. So to you, Toby. Thank you for agreeing to host this session today.
That's okay. I'm happy to do it. So kind of this week and next week, we're going to look at thermodynamics, which is kind of colloquially the study of temperature and how energy flows and how heat flows. So obviously that has lots of applications throughout kind of all of physics, engineering, cosmology. So it's quite an important field. So it uses kind of lots of language, which you're probably used to in everyday life. But as always, in physics, it means something a bit more specific. So kind of the first idea we need to look at is temperature. So in normal life, we're used to using maybe Celsius or Fahrenheit. In physics, we use absolute temperature, which is measured in Kelvin. Now, so Kelvin, 0 Kelvin is absolute zero. So that nothing can go colder than absolute zero. That's the temperature at which kind of all thermal motions, vibrations stop. So that's the minimum temperature. And that happens at 0 Kelvin. And the way to get from Celsius to Kelvin is you just add 273.15. So get from, if you're given a temperature in Kelvin and you want, sorry, in Celsius, and you want to go to Kelvin, you just add 273.15. And because you're just adding 1 Kelvin, kind of the difference, temperature differences are the same. So if something changes by 1 Kelvin, it's the same as changing by 1 Celsius. The only difference is 0 Kelvin is the very lowest temperature you can be. And the other important temperature is room temperature. And this is usually taken to be 20 degrees Celsius. Anytime a question mentions room temperature, it means 20 degrees Celsius, which is equal to 293.15 Kelvin. So that's temperature. The other quantity we need to look at is heat. Now, in normal life, heat and temperature are maybe interchangeable. In physics, they're quite different. Heat is firstly an energy, so it's measured in joules. And for some reason, it's always given the symbol Q. And heat is thermal energy in transit. So this is quite important. Or the word transit here is quite important. So temperature is a property of the object. You can put a thermometer in and you can see how hot or cold something is. Whereas heat is energy in transit. So it tells you how much energy is flowing from one object to another. So it's not a property of the material, but it tells you what process is going on. Okay. So then the final thing we need to look at is, how do we connect these? How do we kind of get between them? We know if there's, if you put something hot next to something cold, heat will flow from the hot thing to the cold thing. So heat and temperature are related. So the quantity we need is something called specific heat capacity. And this is given the symbol C. And so specific heat capacity tells us how much energy, so how much heat you need to raise 1 kilogram of an object by 1 degree or 1 Kelvin. So formula is the amount of heat is equal to the heat capacity times the mass of the object times the temperature change. And so we can see from this that C is measured in joules per Kelvin per kilogram. Okay, so it tells us the amount of energy needed to heat a 1 kilogram object by 1 Kelvin. And this is a property of the material. So it's different for different materials, but also sometimes on how you heat it up, particularly for gases. If you kind of let the gas expand, or whether you keep it in a fixed volume, the heat capacity can be different. But all of the questions we look at today, I think, just look at solids and liquids, where actually the difference doesn't matter. So heat capacity is a property of the material today. The other thing is sometimes, rather than looking at mass, we might look at moles. So this is rather than heat capacity for 1 kilogram of an object, it would be the energy needed for 1 mole, or 10 to the 23 molecules to heat up by 1 Kelvin. Is this all making sense? These are kind of maybe the 3 key ideas we're going to need for the first few questions. Yes. Okay. You may have seen some of these in school. Okay, so let's look at the first question. So we've got a car. Cars weigh about a ton, so 1,000 kilograms. It's traveling at 60 miles an hour and it brakes. And so the brakes, you know, they get hot, so there's heat being created. We're looking at how much heat does this braking process create? Now, just quickly, kind of how do people think we would go about this? Yes, someone says heat is loss in kinetic energy. So the heat gained is equal to the loss in kinetic energy, so it's equal to a half mv squared, which we put the numbers in from the question, so it's a half times 1,000 kilograms times 27 meters per second squared, which, if you want to put that into a calculator, you get about 365 kilojoules, which is quite a lot of energy. Okay. Okay, so the second question. So in winter, so you have to eat to fuel yourself, and part of fueling yourself is you have to keep yourself warm. So in winter, people kind of often find that they get hungrier, and that's because you need to have more food, so you have more energy. So because you need to heat yourself, heat your body up more. So here we're looking at how much, if you eat a Mars bar, how much can you warm the body up with? How much with the energy in that Mars bar? So, what equation would people use to begin this? How do people think they'd start? Yes, everyone's written Q equals MC delta T. Exactly. So we can rearrange this and we get delta T equals Q over MC. So I looked this up, and a Mars bar contains 1 megajoule of energy. So Q is 1 megajoule. M, so this is the mass of a person. I think I haven't given it to you. You can kind of guess. I think I looked it up, and an easy number to use would be about 70. Any number really around there, or more will be fine, really. And then the heat capacity. So the human body is pretty much just water, kind of 70% water. So for this quick calculation, we just assume the body is fully made of water. And the heat capacity of water is 4,200 joules per Kelvin per kilogram. Water's got a really high heat capacity. Metals and things are a few hundred, maybe 600. Water's huge. It stores a lot of heat. So we put these numbers in and we get delta T is 1 megajoule over 70 kilograms times 4,200 joules per Kelvin per kilogram. And if you put this into a calculator, this is 3.4 Kelvin. So it doesn't really warm you up that much. It won't keep you that warm for that long, particularly not on a cold day. Okay. The final question, just looking at heat and temperature before we get into something a bit more complicated. So you've gone out exploring and it's a hot day and you find a nice rock or a nice crystal on the floor and you want to keep it, but it's been baking in the sun all day. So it's got quite hot. So before you put it in your pocket, you can cool it down by putting it in a water bottle with kind of nice cold water. Maybe not the smartest thing to do if that's your only water you've got, but maybe it's a very nice crystal you found. How does the temperature of, what is the final temperature of the rock and the water? So this is maybe a bit harder. So I'll break it down. The rock's hot, the water's cold. So heat flows between them. How do the two different heats relate? So here's a little rock. Here's some water. How do these two heats relate? They are equal, exactly. So Q out of the rock equals the heat into the water. Now, when does this process stop? What is it about the temperatures of the water and the rock that would make this heat flow stop? Yeah, exactly, when they're equal again. So we have the final temperature of the water is equal to the final temperature of the rock. So the heat out of the rock is equal to the heat capacity of the rock times the mass of the rock times the change in temperature. Now, because we're looking at changes in temperature, as I said, we don't need to actually worry about whether or not we're using Kelvin or Celsius, because you just have to add a number. So if you're adding the number to something and then subtracting it again, it's as if you did nothing. So you can use Celsius for temperature differences. So the change in temperature, it goes from 45 degrees Celsius and then to the final temperature. Now, the heat put into the water, the heat capacity of the water times the mass of the water, then the final temperature, and the temperature difference is final temperature minus the initial temperature, which was given in the question. Okay. The algebra at this point is going to get a bit more complicated, but we start by just setting these equal. So we have C MR, 45 degrees C. Okay, then you're going to have to trust me for a step. I'm going to solve this for the final temperature. We want to know the final temperature. So we want to get TF on the left-hand side and everything else on the right-hand side. So then we can plug in numbers. And what we find is we have TF times okay, is everyone happy with this? I moved this over here and then this over here. Okay, then we divide by this to cancel it from the left-hand side. So you have the final temperature is given by and then divided by this factor. Okay, now we just need to plug numbers into the calculator. So the heat capacity of the rock is 700 joules per Kelvin per kilogram. The heat capacity of water, we've already seen, is 4,200 joules per Kelvin per kilogram. The mass of the rock was 0.35 kilograms or 350 grams. And the mass of the water was 600 grams or 600 mil, because it's a gram a mil for water. This is 0.6 kilograms. And then we put all of that together and we get the final temperature is given by 7.6 degrees Celsius, which is equal to 280.8 Kelvin. So water, because it stores so much heat, you need a lot of heat to make it change temperature. The rock cooled down loads and the water didn't heat up very much. If it wasn't dirty, it would probably still be drinkable. Are there any questions about heat and temperature you want to ask before we move on and get swept up in looking at gases? Is there an upper absolute temperature? In general, no. You can just keep putting energy in and things will kind of keep getting faster and faster. I mean, eventually what happens is if you keep heating, things are moving so fast, it basically looks like a gas made purely of light is the very, very hot end of things. And then it just, that kind of gas of light just gets hotter and hotter and bluer and eventually will become kind of ultraviolet and so on. Anything else before we move on? Okay. we'll have a look at the next section. So, I mean, there are lots of different gases. They all behave in very different ways. But the simplest gas you're going to come across, and the one that when I did thermodynamics at university and when I've taught it here at Edinburgh, there's almost always everything is an ideal gas. It's got the nicest equation, and it also includes, it works really well for most gases most of the time, and it already includes kind of all of the physics you need. So unless you want to be really precise, you can just treat most gases as an ideal gas. So what defines an ideal gas is that there's no interactions between different molecules. So as they're flying around, they're just points and they don't interact. There's no like electromagnetic pull between them or anything like that. They just whiz around, not interacting, unless they kind of bounce off the sides of the container. So they point like roughly, and they don't interact, except for very rare head-on collisions, or direct collisions rather. They don't have to be head-on. So this is just point, like billiard balls flying around. And okay, no gas is going to have this perfectly. All molecules have a fixed size, and there's going to be, depending on the molecules, some interactions between them. So in general, something is a good ideal gas if the distance between, so say this molecule's going along, it collides here, and then it flies around, bounces on the sides of the container, and will eventually collide again. If the distance the particle has to travel from one collision before it collides again, if that distance is really, really big compared to the size of the container or any other sizes you care about, then ideal gas is a good approximation. So this distance between collisions is called the mean free path, because it's the average, because, okay, you might get very, very unlucky and hit two things straight away. But on average, it's the distance something has to travel between one collision and another. Free, because it's non-interacting. And then path, just distance traveled. And this needs to be much, much bigger than the size of the container. Okay. Now, the ideal gas law is, this tells us, you may have seen this in school, depending on what exam boards you do. But the ideal gas law is an equation that connects the quantities of the gas together. So you may have seen this, PV equals nRT. It's quite a nice equation. So the different quantities in here, on the left-hand side, you have pressure. And this is measured in newtons per meter squared, or equivalently pascals. We have V, which is volume, which is in meters cubed. Then on the right-hand side, we have temperature. Which is measured in Kelvin. And you have to measure this in Kelvin here. There's no temperature changes. This is just temperature has to be measured in Kelvin. Otherwise, let's say you use Celsius, you can quite easily have negative temperatures there. Well, in that case, if you had a negative temperature, you'd have negative pressure or negative volume, which doesn't really make sense. So if you use Celsius, you'll get not only the wrong answer, but maybe even answers that don't make sense at all. So you have to use Kelvin. I'll put a box around it so we all remember. The other quantities, there's N, which is number of moles. So this is, so 1 mole is 6 times 10 to the 23 molecules. And then finally is this quantity R. And this is called the ideal gas constant. And this is equal to 8.31 joules per Kelvin per mole. Okay. So this ideal gas constant, this equation here will work for air, it will work for kind of hydrogen gases, carbon dioxide gases, nitrogen gases, any kind of most gases obey this, and they all have the same constant. You don't have to look, heat capacity, you have to look it up for different materials. No, ideal gas constant, same for every gas, as long as it is or roughly an ideal gas. Are people happy with this? Or is there anything they want to quickly ask before we look at some questions? So should the, the mean free path will also be much, much greater than the size of the molecules. Has to be bigger than other things as well, depending if there's other length scales in there. But yeah, no, I think you're right. Yeah, I should have said molecules. Or any other kind of important scales going on. Because you're right, if I have one volume and I have another one next to it, and if one ideal gas and another ideal gas, it should be fine, right? If I kind of put them together, or if I suddenly shut the door, so the volume is smaller, it should still be an ideal gas. Just because I shut the door, it doesn't change that. So yeah, thank you. You called me out there. Is there anything else? Okay. Okay, so let's use this in some examples. So kind of you may have seen them in school, so you may have used a vacuum kind of in some experiments, but a really good one in the lab can go down to 10 to the minus 13 pascals. And that's, so standard atmospheric pressure is 10 to the 5 pascals. So we've got 18 orders of magnitude lower than atmospheric pressure. So that's a big pressure difference there. So how many molecules are there per centimeter, per cubic centimeter in this vacuum? So how would we go about looking at this. You're right, PV equals nRT. And kind of what quantity in this, when I look at number of molecules, what quantity in here do we need to find? PV, N or T? N, yes. So N is number of moles, which we can directly relate to the number of molecules. So we have N equals PV over RT. So pressure was given to us, 10 to the minus 13 pascals. Volume is 1 centimeter cubed, which is tiny. It's 1 over 100 cubed meter cubed. And then temperature, well, it's standard room temperature, so that's 20 degrees Celsius. But we've already discussed that we need to use Kelvin. So, and I think, yeah, we mentioned it quite quickly, but 20 degrees Celsius is 293.15 Kelvin. Okay. Okay, so now we put these numbers in and we get N equals 10 to the minus 13 pascals times 10 to the minus 6 meters cubed over 8.31 joules per Kelvin mole times 293 Kelvin. And we put that into a calculator and we get 4 times 10 to the minus 23 moles. Does everyone agree? So now we need to go from this to number of molecules. So to get to number of molecules, which is usually given by capital N, we take the number of moles, we times it by the Avogadro's number, which is equal to times 10 to the 23, and then times 4 times 10 to the minus 23, which is the number of moles. And this just gets us 24 molecules per centimeter cubed. Really isn't very many. Did everyone follow along with this? Are there any questions? Excellent. Okay. Hopefully that means I haven't made any mistakes in the plugging numbers into my calculator the other day. Okay, so problem 5. There's a bit of a challenge at the end. We'll see if we kind of want to do it, but we'll focus on the first 3 bits. So in this question, we're looking at why is a freezer kind of, do you have to give it quite a lot of force to open it? So, I mean, the reason is, as the air cools down inside, there's much less pressure from that air, and there's quite a big pressure from the outside. So when you pull on a freezer door, you're having to overcome the extra pressure from the outside compared to the inside. Okay, so before the freezer is turned on, what is the mass of the air inside the freezer? I'm assuming it's empty. There's no kind of food, which is mainly water in there. So it's just an empty freezer. And I haven't turned it on yet, so it's all at room temperature. So how do I get the mass of the air inside? Again, PV equals nRT. And we want to get mass. We can relate that to N. So the mass is equal to the molar mass times the number of moles. So the molar mass is, you may have seen this before, but they're just the mass of 1 mole. And have I given it? Yes. And I've said for air, it's 28 grams per mole. So we have N equals PV over RT. Now, atmospheric pressure is 10 to the 5 pascals. The volume is 1 meter times a half times a half. So that's 0.25 meters cubed. R, as always, 8.31 joules per Kelvin mole. And then the temperature is 293.15 Kelvin. We put that in, and we have there's 10.3 moles in the fridge. Well, sorry, in the freezer. Then, so in order to get mass, we multiply it by the molar mass. So M equals 28 grams per mole times 10.3 moles, which it's probably easier to work in kilograms. So we have 0.028 kilograms per mole times 10.3 moles. And overall, this gives us a mass of 0.29 kilograms. So that's the amount of air if you just had an empty fridge or empty freezer and just shut the door. That's the amount of air that's in there. Okay, so now we turn the freezer on and it's going to suck heat out of the air and cool the air inside down. So how do we relate there's 2 steps here. So the freezer withdraws 100 watts of power from one of the mains, from the plug. and it's got an efficiency of 75%. So efficiency is the amount of heat taken out of the air in the fridge divided by the amount of power taken from the mains, the electricity used. So, sorry, the rate of power, that should be rate of heat extracted. So this implies the rate of heat out, so it's the rate at which heat extracted, the amount of heat per second, is given by power of the fridge, or the power of the freezer rather, times the efficiency, which is 100 watts, times 75% efficient, which is equal to 75 watts. Okay, now how do we work out, probably begin working out how long this takes to cool down. So I think, what does the question say? It says, cool down to a freezer temperature. Freezer's going to run at minus 18 degrees Celsius. So how would we get the amount of heat needed to extract in order to cool the air in the freezer down from room temperature to minus 18 degrees Celsius? Which equation would we use? Yes, so you've all put the total amount of heat needed is equal to MC delta T. Okay, so we've already calculated the mass. C is given to us in the question, and delta T, we're going from 20 degrees Celsius down to minus 18 degrees Celsius. So that's a temperature difference of 38 degrees, which is equal to 38 Kelvin, because it's a temperature difference. Okay, so the total amount of heat needed is therefore the mass, which is 0.29 kilograms, times 720, which is the heat capacity, joules per Kelvin per kilogram, times 38 Kelvin. Now, did I write this down? Yes. Put all these numbers in, and you should get 7,934 joules. Now, finally, we want to work out how long it took to cool down. So we've got the total amount of heat used, and we've got the rate of heat extracted. So how do we use this to get the time taken? Yeah, someone said divide by 75. Yes, I think what you mean is correct. So the time is equal to the total amount of heat needed divided by the rate at which we extract heat, which is equal to 7,934 joules divided by 75 joules per second, which is 102 seconds. At least that's what I've got written down. Okay, so it takes really not that long to cool down. In reality, as you get colder, it's going to be harder and harder to kind of cool down the air inside the freezer. The cooling section is going to be at one part in one kind of bit of the freezer. So it's, you might not get these nice currents. You might have a cold section, so it can't cool it down. Then you've got a warm section over there, and it takes time for the heat to flow across. And as soon as you put food in, you put a couple of kilograms of water in there, which is what would happen if you put some leftovers or a chicken in. Suddenly you need to take out loads and loads and loads of heat to cool it down even a little bit. You've got loads of huge mass of water, and water's got a high heat capacity. So as soon as you put food in there, it's going to take a lot longer than just empty air. Okay. Now, what is the pressure on the door, both inside and outside? So, who remember, what is the pressure outside of the door? Yeah, 100 kilopascals. So pressure is 10 to the 5 pascals. Inside, as always for this section, we're going to use the ideal gas law. Pressure, PV equals nRT. Which means pressure equals nRT over V. Okay, so N we've already calculated up here to be 10.3 moles. The volume we've calculated to be 0.25 meters cubed. The temperature is minus 18 degrees Celsius, which is, where have I got it written down? Oh, I didn't write this down, but so we need to get this into Kelvin in order to use the ideal gas law. So we have minus 18 degrees Celsius plus 273.15, which I'm going to have to use the calculator in real time here. 273.15 minus 18 is 255.15 Kelvin. Okay, now we plug all these numbers in. So we have 10.3 times R, which is 8.31. The temperature, 255.15 over 0.25. And everything in the end will end up pascals. And we end up with 8.7 times 10 to the 4 pascals. So actually, we've got quite a big pressure difference. If this was a perfect refrigerator or a perfect freezer, so all of the air inside was minus 18, there'd be a huge pressure difference. And it would take a lot of force. they did it when going through, and it's like 1,000 newtons or a couple of thousand newtons in this ideal example to open the freezer. In reality, things won't be exactly down to temperature. There'll be little air pockets, so things seep in and out. We've assumed everything's perfect, and life never is. But I will leave the final bit to you. It requires you to remember all your mechanics. Okay. Are there any final questions about kind of ideal gases before we start looking at kind of what's called molecular kinetic theory, which is how the molecules in a gas behave? Okay, are there no questions? In which case, we'll look at molecular kinetic theory, which is the last part for today. Okay, so you're probably all aware that, so a gas, there's molecules flying around. But molecules can also do other things if you give them energy. Depending what they do, they can, you know, if there's like oxygen, which is two atoms stuck together like this, they can spin round. If you really heat them up, they can start to vibrate, but you need loads of energy to get that to happen, usually. It takes so much, you need to really, really heat them up before they can start to wiggle. So that very rarely, that doesn't happen at room temperature. So kinetic theory allows us to calculate, if we know the temperature, how much energy do these molecules have? And we're not going to be able to prove this formula in any way, but the result is the equipartition theorem. And this says the average, right, because we're always dealing with averages in thermodynamics. So I'll write that neater. I couldn't even read it. Average energy per molecule per degree of freedom, and we'll get to what that means in a second, is a half kBT. So there's usually a little k. So we say big K, the Kelvin, and this here is a little k sub b T. And this is what's called the Boltzmann constant. And it's essentially the ideal gas constant for a single molecule. So we'll get back to that in a second. I think the first thing to look at is degree of freedom. So this is the amount, what things can the molecule do that contributes to its energy. So we've already discussed, this is our gas molecule, my calculator. It can go back and forth, so it can move around. That's 3 degrees of freedom. And then depending on the molecule, it can maybe spin round or something. So these are extra degrees of freedom. We will have a look. We'll look at an example in a minute where we're going to calculate this explicitly and look at different gases and to see what that means. So this Boltzmann constant is kind of equivalent. It's very, very similar to the ideal gas constant. It's got the same units. The difference is, so the relation is the ideal gas constant R is equal to the Avogadro's number times the Boltzmann constant. So in other words, ideal gas constant is for 1 mole. The Boltzmann constant is for 1 molecule. So we can rewrite. There's a bit of a tangent, but it might be useful. So we can rewrite the ideal gas law as PV equals big N kBT. With this here, rather than number of moles, is number of molecules. And we can use this to calculate the Boltzmann constant. So the Boltzmann constant is 8.31 joules per Kelvin per mole divided by 10 to the 23, or 6 times 10 to the 23, and we have 31 over times 10 to the power 23, which is equal to 1.39 times 10 to the minus 23 joules per Kelvin. Okay. Okay. And then the final thing we're going to do, because we're so used to using moles, we're going to rewrite the equipartition theorem in terms of moles instead. So rather than energy per molecule, let's look at energy per mole. So that's given by Na times a half kBT, which is equal to a half RT. So in other words, if we have 1 mole of a substance instead of 1 molecule, this is the amount of energy per degree of freedom. This is maybe quite a lot. This is going to be a difficult concept, the equipartition theorem. So are there any questions before we move on? If not, I might just let it sit for kind of 30 seconds or so, just so you can absorb it. I mean, maybe what's extraordinary is that every degree of freedom here, so everything a particle can do, the energy just depends on temperature. So this means that the kinetic energy of a molecule doesn't depend on its mass. It just depends on the temperature. The speed of the molecule will depend on the mass, but the kinetic energy doesn't depend on temperature. Okay. So the question is, look at what is the average thermal energy in 1 mole of a gas of a diatomic molecule like oxygen. So oxygen is O2. And compare that to with a monatomic gas. And the standard example is argon. It's in light bulbs and things, but any of the group 8 elements, they're inert. They don't interact. They're always just monatomic gases. So let's start looking at the monatomic gas. So it's just this, just a point. What can this do? Does anyone have a guess of how many degrees of freedom does just a monatomic gas have? Three. Yes. So if we look at the energy, the kinetic energy, what's the energy of this one molecule? It's a half Vx squared plus Vy squared plus Vz squared. So you're right, there are 3 degrees of freedom here. And so, using the equipartition theorem, 1 mole is a half, is 3 times a half RT equal to 3/2 RT. And you may have seen this. Again, different examples do different things, but some people do ideal gases in their A levels. You may recognize the energy of an ideal gas here. It's 3/2 RT. Now, what about oxygen? Now this looks like this. So it's two atoms attached to each other. How many degrees of freedom do you think this has? And it's really not obvious. I didn't get this right the first time I saw it. Or maybe even the second and third. How many degrees of freedom do you think this has? Someone is saying 6. What do you think those degrees of freedom are? So you're right. So there's a lot fewer than, there's actually 5. I'll write the answer down. There's 5 degrees of freedom. And we'll have a look at why. It's really not obvious. I was confused the first time I saw this. So there is the 3 directions the whole molecule can move in. So we've got a half Vx squared plus Vy squared plus Vz squared. So we've got the translational kinetic energy. Then it can rotate. So now there's only 2 directions it can rotate in. So it can rotate along the green axis, so it's spinning in around there. It can rotate along the blue axis, but these particles are point-like. So there's no rotation around this direction. No. So because these particles are point-like, it can't spin in that direction. If it could, we'd have to include rotations of this as well. So because it's the same, no matter how you twist it, there's no way of knowing it's rotating. It doesn't rotate at all. Yes, so I thought this would confuse people. So a degree of freedom is basically an independent thing, an independent quantity needed to specify what the particle or what the molecule is doing. And I think there's one thing that's important here. Per degree of freedom that contributes to the energy. That's important, hidden away. So it's an independent value, an independent thing quantity that is in the energy. So for here, for just a single point particle, the energy just depends on the velocities in each direction. So we have x squared, vx squared, vy squared, vz squared. So there's only 3 quantities here. If you just want to look at, if you want to look at oxygen, here we've got, so the whole thing can move around. So there's 3 degrees of freedom there, which is again the vx squared, the vy squared, the vz squared. Plus rotations. So there's actually only 2 rotations. Because it's just a point, there's no way of knowing kind of how it's rotating along its axis. It doesn't, because it's just a point, it can't rotate this way. And so there's only 2, which are the rotations in this way and the rotations in this way. The other way of seeing that is, so the rotational kinetic energy is a half I, which is the moment of inertia, times omega squared, so the angular speed. X. But because it's just a point along the z-axis, around this axis is just a point, this here is 0. So actually there's only 2 degrees of freedom, only 2 rotational degrees of freedom. Or then you could also say it's vibrating. But we've discussed earlier that things have to be really, really hot before it can start vibrating at all. So actually, a molecule at kind of standard temperatures is just fixed, it's rigid. It can't do anything else apart from move and spin. So we see here, how many quantities are there? 1, 2, 3, 4, 5. So energy of 1 mole is equal to 5/2 RT. Is this making sense? There is more information, and it goes to a kind of a similar example on the sheet, but yeah, it definitely wasn't obvious to me the first time I saw it. And sometimes working them out isn't easy. I mean, a side question that's not, I haven't written as an actual question. Which of these do you think would have the higher, which one of these would require more energy to heat up? So which one would have probably the higher heat capacity? Just from looking at this, if this was argon and oxygen, say. So if you see that for a given temperature, oxygen has much more energy than the monatomic gas. So in order to heat up oxygen, because it has more things it can do, there's more places for that energy to go, you will need so much more energy in order to change its temperature. And then you go to something like water. So water has a really high heat capacity. And that's because it has there's so much a water molecule can do. It looks like this. So it can spin in 3 directions. So it can move around, it can spin in all directions. The little Mickey Mouses on water, the hydrogen atoms, they can wiggle as well. And it's also quite light. So you get loads of water molecules in a given, for 1 mole, there's actually loads of them. So it has a huge heat capacity. Sorry, 1 kilogram of water has loads and loads of molecules. So water has a really high heat capacity. And this equipartition theorem maybe gives us a hint to why. Okay. We've got about 15 minutes left and we're on to the last question. So a light bulb. So normally just ordinary filament light bulbs, they normally contain argon because it's inert. When the metal wire heats up, it's not going to interact with the argon. It's not going to rust or something like that. For oxygen, it would rust pretty much instantly. So, however, just for the question, we've got a light bulb that contains neon and argon. Maybe they wanted to glow a different color. Different gases would do that, or might do that. So we have our light bulb, and a small crack appears. And the gases can leak out slightly. So what ratio? So the light bulb has 50%. So 50% of the molecules are argon, 50% are neon. What ratio are the gases that kind of come out the crack? Does anyone want to have a quick guess whether more neon or more argon will come out, given that the argon molecule is heavier? Will more neon or more argon come out? Yes, exactly. So neon would come out. More neon would come out. There's the same amount in there. They have the same kinetic energy because we've already seen kinetic energy doesn't depend on mass. But because neon is lighter, it can move faster. Exactly. So let's zoom in to this crack here. So we have like this. Let's say the crack has area A. Then we can use the equipartition theorem. So each degree of freedom, as we said, has the same energy. So if you say this is the x direction, what's going to determine whether a molecule comes out is whether or not, so let's say we look at a fraction of a second, so in a time delta t, whether or not a particular molecule is going to come out of this crack or not is its x velocity, Vx, is it fast enough such that Vx times the time is bigger than this distance here. So in other words, we kind of think about this a different way. In a time delta t, the amount of gas, the molecules that, the gas molecules that come out are those in this region here, which are inner length Vx delta t. Obviously, this is all averages. So not all of them will, but obviously some will go over here, but just as often some will come this way. So as a quick guess, any molecule or that's in this region, or sorry, half the molecules, obviously half will be going in the other direction, so they won't go out no matter how fast they're going. But the molecules in this green area here will leak out. Okay, so let's have a look. So let's calculate how many molecules come out for argon and neon. So let's call this distance L. So the number of molecules that come out, big N, is equal to the number of molecules per unit volume. So I'll call this N molecules. So this isn't number of moles, this is number of molecules per unit volume. Times L times the area of the crack. So this is the volume of this green section here. So I'll put a little green box around it to mirror. And also we discussed that there'll be an extra factor of a half, because half the molecules are going in the other direction. So this L is given by Vx delta T. Now, using the, I think someone kind of mentioned it, we can get Vx from the kinetic energy. So we have a half m Vx squared. Well, this is m is mass of one molecule, is equal to a half Kb times the temperature. So Vx is equal to the square root of kBt over m. We only need a half kBt, even though these have 3 degrees of freedom. We only care about the x kinetic energy. So we only need to look at that 1 degree of freedom. The other degrees of freedom are doing their own thing. They don't affect this. So Vx here, so L is equal to root of kBt over m delta t. So if we want to calculate the amount of neon compared to the amount of argon, So the number of neon molecules divided by the amount of argon molecules. We use this formula here. It's a big one in the middle. Except we have to sub in here for the particular molecule we're interested in, as we'll see. So we have a half times area times number of molecules times this L, which was given by root KBT over M delta T, where this M of neon, not meon, neon. Okay, and now for argon, the exact same. Now we said there's the same number of molecules of argon and neon in the light bulb. So these ends are the same. They cancel. The area of the crack is the same for both gases. A half is just a half. The time we're looking at is the same. KB is just a constant. Both gases, they're in the light bulb together, so they're at the same temperature. So all of these things cancel out. All that matters is the masses of the molecules. So we have the square root mass of the argon divided by mass of the neon. So we have these masses, or we have the molar masses here. We want to get these masses in terms of these molar masses, who are one step away. I'll explain that in a minute. I'll finish this. We're one line away, then I'll get to the question. So we put these in. We want to get molar masses. So the molar mass is equal to the mass of one molecule times Avogadro's number. So let's do mass of argon times Avogadro's number divided by mass of neon times Avogadro's number, which is equal to mu of argon divided by mu of neon, which the molar mass of argon is 40, the molar mass of neon is 20. So this just becomes root 2, which is about 1.4. So we see for every 10 argon molecules that come out, 14 neon molecules come out the crack. Are people happy with the question? Obviously, there'll be time to look through it when you see the sheet and kind of think about these things again. So there's a question in the chat, which is, why does each degree of freedom have the same energy as the others? Why is... it's a good question, and kind of really to prove it mathematically, you'll need to do quantum physics, and then you'll need to do statistical mechanics, which is kind of a second or a third year course. But there is a... It's essentially, let's say I heat up the gas. I'm putting energy in. And the energy can become kinetic energy, like translational kinetic energy, or it can go into spinning the molecule. Well, as I put energy into the gas, the energy is going to be evenly split between moving the molecule around and spinning it. it would, in many ways, I mean, if say it all went into one type of energy and not another, there's got to be a reason for that. And if there's nothing stopping the molecules spinning or moving in different directions, well, the energy is going to be kind of evenly split between the different things it can do. If there was something stopping it, like if you had like graphene, which is 2D, and you heated up kind of the electrons in there, they could only move in 2 directions. They couldn't move in 3, so they'd only have 2 degrees of freedom. But essentially, the reason they all have the same is you heat up the gas, it's going to go into all the different things it can do equally. Are there any other questions? Okay, is there anything else? We have 1 minute till time's officially up. Are there any final questions or? Okay, well, I think that's everything I had planned. We'll be looking kind of next week, we'll be looking at using kind of these ideas. We'll be looking at engines and how energy, kind of both heat energy and mechanical energy get included here. We kind of, but that's next week. I don't know if he's coming back to end the call, or if not, I mean, thank you all for coming and have a good Easter, and I'll see you all next week.
Thank you very much, Toby.
Okay.
All right, thank you, and yeah, see you next week.
Bye-bye.
Bye.